Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. In the evolving landscape of IT and networking, virtual environments are becoming the new standard. Physical hardware still plays a crucial role, but increasingly, core network functions are being replicated, abstracted, and controlled through software-defined components. Among the most critical of these components are virtual network interfaces and the broader ecosystem of virtual networking architecture. These tools enable seamless communication between virtual machines, integration with physical infrastructure, and flexibility that traditional networks cannot easily match. They are foundational to any data center, cloud deployment, or enterprise virtualization strategy. Virtual network interfaces simulate the function of physical network components, like switches, routers, and NICs, but exist entirely within the hypervisor or virtualization management software. These virtual devices allow data to flow between virtual machines, VMs, between VMs, and the physical world, and even across geographically separated locations. Without virtual interfaces, virtual machines would be isolated entities with no ability to participate in wider network operations. For modern IT networks, they are not an add-on or convenience, they are an essential part of the infrastructure. The Network Plus exam includes coverage of virtual networking and its virtualization and infrastructure objectives. You are expected to recognize the terminology, understand the function of virtual NICs and virtual switches, and distinguish between internal-only virtual communication and traffic that crosses the boundary into the physical network. This knowledge is not only important for certification success, but is also directly applicable in nearly every modern enterprise environment, from local test labs to massive cloud-based architectures. The most fundamental building block in virtual networking is the virtual NIC, or network interface card. This is a software-based emulation of a physical network adapter. Every virtual machine is assigned at least one virtual NIC, just as a physical computer would have a physical NIC. These virtual NICs are how VMs send and receive packets, whether within the same host, to another VM on a different host, or out to the internet. The hypervisor mediates all traffic, translating the virtual NIC's data into a format that can be handled by the underlying hardware. Virtual NICs have configurable parameters just like their physical counterparts. You can assign them static IP addresses, or they can obtain IP addresses via DHCP. They also have their own MAC addresses, which may be dynamically generated or manually assigned. In some environments, MAC address spoofing or duplication may become an issue, which is why many hypervisors allow for MAC address controls and monitoring. Because each virtual NIC is software-defined, it can be modified or replaced without shutting down the VM, adding to the flexibility and manageability of virtual systems. To connect virtual NICs to each other and to the rest of the network, virtual switches are used. A virtual switch, or vSwitch, is a Layer 2 device created and managed within the hypervisor. It operates similarly to a physical switch. It receives Ethernet frames from connected virtual NICs and forwards them based on MAC address lookup. The virtual switch can be configured with VLANs, access controls, and security settings to isolate traffic and protect segments. Some advanced platforms also support distributed virtual switches, which span multiple hosts and allow for consistent policy enforcement and centralized management across clusters. Virtual routers and gateways operate at Layer 3 and provide IP routing between different virtual networks or VLANs. These devices may be deployed as full-featured virtual appliances, such as virtual firewalls or cloud gateways, or as lightweight software-based routers running on hypervisor platforms. They perform all the duties of physical routers: NAT, DHCP, routing protocol participation, and traffic forward. These virtual routers can be dynamically resized or reconfigured to meet changing network demands, which is especially useful in environments that scale rapidly. In virtual environments, IP address assignment is handled with a high degree of flexibility. A virtual NIC can be manually configured with a static IP address or can obtain one from a DHCP server. Depending on the network design, DHCP services may be provided by a physical server, a virtual appliance, or even directly by the hypervisor. Bridging, NAT, and isolated modes are commonly available in hypervisors to control how virtual machines access outside network. Bridging makes the VM appear as a peer on the physical LAN, while NAT allows the VM to access the internet using the host's IP, and isolation restricts communication entirely. VLANs are fully supported in virtualized environments and serve the same purpose as they do in physical networks, segmenting traffic by role, department, or function. Inside a virtual switch, VLAN IDs can be assigned to specific virtual NICs, tagging their traffic appropriately. The virtual switch handles the VLAN tagging and ensures that frames are placed on the correct segment. This setup requires coordination with the physical switch if the traffic leaves the hypervisor, ensuring trunk ports and VLAN IDs match across both domains. The distinction between internal and external virtual interfaces is essential to understanding traffic flow in virtual networks. Internal virtual interfaces connect VMs to each other within the same host or cluster. These interfaces do not route traffic outside of the virtualized environment. They are ideal for services that only need to communicate internally, such as application and database servers within the same tier. External interfaces, by contrast, connect to physical NICs and allow traffic to leave the virtual environment. These are essential for internet access, cross-site communication, or integration with physical infrastructure. Loopback interfaces are another virtual network feature, often used in complex architectures. A loopback interface is a software-only interface that is always up, regardless of the state of any physical hardware. They are used in routing and network monitoring, especially for services that require a stable, consistent endpoint. For example, a router may use its loopback interface as the source of OSPF or BGP traffic. In a virtual environment, loopbacks provide diagnostic capability and are often assigned to core services that need to remain reachable regardless of network topology changes. Tunneling and encapsulated links are commonly used in virtual networking to enable communication between systems located in different physical or cloud environments, and IPsec tunnels can be built over virtual NICs, allowing virtual machines in one site to communicate securely with those in another. These tunnels encapsulate packets in an additional IP header, making them transparent to the intermediate networks. Tunneling is essential for multi-site VPNs, cloud hybrid networks, and secure overlays in environments with multiple isolated segments. Finally, virtual firewalls and appliances play a key role in regulating traffic inside virtual networks. These are software-based devices that operate just like traditional firewalls, but are deployed as virtual machines. They inspect packets, enforce security policies, manage NAT, and control access between networks or VLANs. Virtual appliances may also include intrusion detection systems, proxy services, or traffic shapers. Their placement is strategic. They are positioned between virtual networks to segment and protect services, and can scale with the environment as needs change. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other podcasts on cybersecurity and more at baremetalcyber.com. Virtual network interfaces offer a wide range of benefits that make them an essential part of modern infrastructure. One of the most compelling advantages is the speed of provisioning. With physical infrastructure, adding a new network connection might involve running new cables, installing hardware, and configuring ports. In a virtualized environment, the same result can be achieved in minutes, simply by creating a new virtual NIC, connecting it to a virtual switch, and assigning an IP address. This rapid deployment supports agile development, testing environments, and dynamic scaling in response to demand. Flexibility is another major benefit of virtual interfaces. Reconfiguration is as simple as editing settings within the hypervisor or orchestration platform. You can easily change VLAN assignments, reroute traffic, or isolate services without touching a single physical cable. This flexibility reduces downtime, simplifies migration, and supports high availability. Combined with virtualization's inherent mobility, where VMs can move between hosts, this flexibility ensures that the network can keep pace with evolving application and business requirements. Cost savings are also a significant factor. Virtual interfaces reduce the need for physical switches, patch panels, and network interface cards. By maximizing the usage of each physical host's NICs and distributing those connections among many virtual machines, organizations minimize their hardware footprint while increasing efficiency. This leads to lower equipment costs, reduced energy consumption, and simplified rack management, all of which contribute to a leaner and more cost-effective IT environment. Virtual networking doesn't operate in isolation. It must integrate seamlessly with physical infrastructure. Virtual switches connect to host NICs, which in turn link to physical switches and routers. This physical-to-virtual integration allows virtual machines to communicate beyond the hypervisor, access shared storage, or reach the internet. In many environments, virtual switches are configured to trunk VLANs, just like physical switches. This enables a unified VLAN architecture across virtual and physical domains, maintaining consistent segmentation and policy enforcement throughout the network. At the host level, network configuration can become quite sophisticated. Hypervisors often support NIC teaming or bonding, which combines multiple physical interfaces into a single logical interface for increased throughput and redundancy. These features are particularly useful in environments that require high bandwidth or failover protection. Hosts may also require specific interface settings, such as speed and duplex configurations, to ensure optimal performance and compatibility with upstream switches. Bridging modes determine how traffic flows between virtual and physical networks. Options include NAT, bridged, and host-only, each with unique behaviors. To configure and manage virtual network components, administrators rely on a variety of tools. These range from hypervisor-specific interfaces, like VMware vSphere or Microsoft Hyper-V Manager, to cross-purple orchestration tools such as OpenStack, Proxmox, or Red Hat Virtualization. These tools offer graphical and command-line interfaces that allow for the creation, modification, and monitoring of virtual switches, NICs, firewalls, and more. Centralized dashboards simplify the management of large environments by offering unified visibility across hosts and networks. Monitoring virtual traffic is another critical consideration. Because much of the data in a virtual environment never reaches a physical wire, traditional network monitoring tools may not detect it. This has led to the development of virtual taps, port mirroring features, and deep integration with monitoring systems like vRealize Network Insight, Wireshark, or SolarWinds. These tools allow administrators to capture traffic between virtual machines, analyze flow patterns, identify bottlenecks, and detect anomalies, all without disrupting service. MAC addressing in virtual environments presents both advantages and challenges. Each virtual NIC is assigned a MAC address, typically by the hypervisor. These can be either dynamically generated or statically assigned, depending on the configuration. Some hypervisors regenerate MAC addresses when a VM is moved or cloned, which can lead to conflicts if not properly managed. In environments that rely on MAC-based filtering or security policies, maintaining consistent and predictable MAC addresses is essential to avoid connectivity issues or unauthorized access. Despite their benefits, virtual network interfaces do introduce challenges. Troubleshooting layered connections can become complex, especially when traffic passes through multiple virtual switches, bridges, and tunnels before reaching its destination. A misconfiguration in any layer, such as an incorrect VLAN tag, disabled virtual NIC, or misassigned MAC address, can cause symptoms that are difficult to trace. Furthermore, resource contention on the host, such as oversubscribed physical NICs, can degrade performance across all connected VMs. MAC address conflicts are a notable concern in environments where static MACs are reused or when VM cloning procedures are not properly managed. Duplicate MAC addresses can cause unpredictable network behavior, including frame delivery errors and loss of connectivity. Hypervisors often include safeguards against this, but administrators must be aware of how MACs are assigned and how to control them, especially in larger multi-tenant environments where many systems operate simultaneously. Resource contention is another challenge. Since virtual NICs share the underlying host NIC, bandwidth can become a bottleneck if too many VMs are sending or receiving large volumes of traffic. Administrators must monitor usage and, when necessary, allocate bandwidth through quality of service (QoS) settings or spread workloads across multiple hosts. Some hypervisors support traffic shaping policies that can limit or prioritize specific types of traffic to ensure consistent performance across virtualized services. On the Network Plus exam, expect virtual networking to appear in several forms. You may be presented with diagrams showing both virtual and physical components, and asked to identify which ones represent virtual NICs, switches, or firewalls. Questions may test your understanding of how virtual machines obtain IP addresses, how VLANs are implemented in virtual switches, or what happens when a virtual NIC is disabled. The exam may also include scenario-based questions where you must troubleshoot a connectivity issue within a virtualized environment. Understanding the difference between virtual and physical roles is essential for both the exam and real-world environments. For example, knowing that a virtual firewall can be placed between VLANs within a hypervisor and that it controls traffic entirely in software changes how you approach segmentation and security. Similarly, recognizing that VM-to-V communication on the same host might never leave the hypervisor can influence how you design monitoring or enforce data loss prevention policies. In summary, virtual network interfaces and their associated components are foundational to modern networking. They provide the flexibility, scalability, and manageability required to support dynamic workloads, cloud services, and complex application architectures. While they mirror the concepts of physical networking, they operate in ways that offer new possibilities and new responsibilities for IT professionals. Mastery of these virtual tools equips you to build, maintain, and troubleshoot networks that are agile, efficient, and ready for the demands of modern business. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.